This is the study session on quantitative methods and the reading on hypothesis testing. Let's get right to the slide deck and the LOS. First one asks us to define a hypothesis, to describe steps in hypothesis testing, and then describe null and alternative hypotheses. So the first question we need to ask is, what is an hypothesis? Let's go ahead and put together a definition. It's an assumptive statement. That means that we're making some assumptions, and then we're going to make a statement about some state of the economy that we believe in. It could be an opinion, could be a personal belief, it could be a belief based on professional experience. For example, a financial analyst might put together a hypothesis that sounds like, I think that alternative investments will outperform traditional passive index funds for this coming year. Another good investment example I have right on the slide deck there. The mean return of a small cap stock higher than that of a large cap stock. But of course, hypothesis testing is not confined to the investments arena. You could extend this into the world of sports. One could say something like, I think Tiger Woods is going to win the Masters next year. That's an opinion. I think Tom Brady is going to win yet another Super Bowl. Now, the next step then is to try to formalize that set of beliefs or that opinion into a process under which we can collect some data and then make some reasonable conclusions regarding that null hypothesis. I mean, if someone said to you, I think Tiger Woods is going to win the Masters next year, you might think to yourself, hey, that has a pretty good chance of occurring. And then someone else said to you, hey, you know what, I think Jim is going to win the Masters next year. And of course, I'm a terrible golfer and I have no chance of winning any golf tournament, let alone the Masters. And so that kind of a hypothesis is not really relevant. But the Tiger Woods hypothesis, we can actually collect some data. And that's what we're going to do with the next part of the LOS in identifying the steps. State the hypothesis. Select the appropriate test statistic. You should remember from previous readings, we had discussions on Z statistics and T statistics. We're going to learn about chi-squared statistics and F statistics. We need to identify the level of significance. Let's go back to my example here. What chance do you think Tiger Woods has of winning the Masters next year? Maybe 20%, maybe 25%. What chance do I have? I have a 0% chance. So what we need to do is identify a level of significance that has meaning. Maybe like 95%. Remember in a previous reading you talked about 95% confidence intervals? Well, that level of significance in the previous reading applies as well in this reading. State the decision rule regarding the hypothesis. So we're going to be able to say something like, if this happens, then we're going to reject our hypothesis. Collect some sample statistics, some sample data, and then compute the sample statistic, and then make a decision regarding the hypothesis. Nobody has to say, you know what, you're crazy to think that Jim is going to win the Masters next year. But you might say something like, boy, I can say with 95% confidence that Tiger Woods is going to win the Masters next year. All right, the last part of this first LOS asks us to differentiate between the null and the alternative hypothesis. The null hypothesis, which is always noted as uppercase H, 0, H-O, represents the current state of knowledge about the population parameter. That's the subject of the test. For example, something like, let me go back here, the mean return of the small cap stock. We could put it in that kind of a formulation. And so the null hypothesis can be set up to be either a one or a two-tailed test. If there's an equal sign in between the two means, that's a two-tailed test. And if there's a greater than or less than or equal sign, then that's going to be a one-tailed test. And so our null hypothesis could be, what was that first one I gave you? I think that the returns on alternative investments are going to be greater than the returns on a passive equity index fund. That would be the null hypothesis. Then the alternative hypothesis would be just the opposite. Now here's some good pictures of one and two-tailed tests. So look at the bottom of the slide. There are three normal distributions. On the left, there's a two-tailed test because right in the middle, that's the mean. A two-tailed test means that we're worried about going in both directions. And so the alternative hypothesis in a two-tailed test is always going to be that they are not equal, which means they could be greater than or less than. So we need to split the significance up into each tail. So if we have a 5% level of significance, we're going to throw 2.5% on the left tail, 2.5% on the right tail. That's a two-tailed test. On the other hand, a one-tailed test, we're going to put everything in the left-hand tail or everything in the right-hand tail, and that's where the blue shaded region comes in. My example about the alternative investments offering superior performance, that would be a one-tailed test. All right, so what were those steps back there? Let's go ahead and compute a test statistic. And so this LOS asks us to explain a test statistic and then do a couple other things that we'll do in the next slide or so. A test statistic is simply a quantity calculated based on the data collected in a sample. And that value is going to be used in determining whether or not we reject or accept the null hypothesis. And the test statistic is a simple formula. You have the sample statistic in the numerator, subtract out the hypothesized value, and then divide by the standard error. So I want you to get a sense of this test statistic, just like in previous readings, is that it's really kind of like always some mean in the numerator, or at least a mean difference in the numerator, divided by some form of variability, like a standard error in this case. Examples are z and t from previous readings, and we'll do chi-square later on in the slide deck. What we'll do is we'll divide these test statistics and compare them against critical values, and we'll get something called a rejection region and an acceptance region. How about type 1 and type 2 errors? These are important here. So explain type 1 and type 2. So let me go ahead and read these real quick, and then I'm going to give you a good example. Type 1 error is when we reject a true null hypothesis. Type 2 error is the failure to reject a false null hypothesis. And those of you who are football fans will see this every Saturday and every Sunday, whether you're college football fans or professional football fans. What happens? There's a play, and one of the football players either makes a catch or dives into the end zone, and the refs say, touchdown. That's the null hypothesis. The null hypothesis is, hey, there is a touchdown on that play. But then what happens? The opposing coach, whose defense was trying to prevent the touchdown, says, wait a minute, I don't think that was a touchdown. So he throws the red flag out onto the field, and they review the play. So the alternative hypothesis is that there is no touchdown. And so then what happens? We go to the video, and the announcers, we watch it 600 times. The announcers have an opinion. They bring in a ref, and a former ref comes on and gives his opinion about whether or not this is going to be overturned. And so what happens then? What generally happens is that the ref comes up and says, the play stand, it's a touchdown. But sometimes the ref will come out and say, wait a minute, you're right, it was not a touchdown. So what's a type 1 error? That's when we reject a true null hypothesis. That would occur when there was actually a touchdown and the ref sees something on the video and says, no, that was not a touchdown. Type 2 error is failure to reject a false null hypothesis. And so you can go through the whole touchdown example again to get type 1 and type 2 errors. Level of significance represents the probability of making that type 1 error. Now, what is the decision rule? Procedure followed by analysts and researchers when deciding whether or not to reject or accept the null hypothesis. We use the phrase not to reject because it's considered statistically incorrect to accept the null hypothesis. But lots of people use reject and accept as opposites. But statistically, econometricians will say you either reject or you do not reject. And of course, prior to the test, there should be a determination of whether or not it's one-tailed or two-tailed. All right, so case one, a left-hand or a left-sided one-tailed test. What we're doing is we're suggesting our idea or our opinion is that the parameter is less than x. If it's a right one-tailed test, then we're suggesting or believing that the parameter is greater than x. And if it's a two-tailed test, we're going to suggest that the parameter is not equal to x, which means it could be greater than or less than. And in order to make the decision, we need to compare our test statistic to a critical value. So notice, let me go back here. If we go back to our case one, there's the words critical value in there. Case two, critical value. Case three, 2 times we have the words critical value in there. Now those critical values are going to come from the tables, either the z tables or the t tables with the chi-square or the f tables. I'll show you that in just a little bit. And what we're really going to do is just compare two numbers. So the concluding statements that we make are going to be based on the relationship between the test statistic and the critical value, and it's really a determination of which one is greater than the other. Now, the power of the test gives the probability of correctly discrediting and rejecting the null hypothesis when it is false. Now, what about the difference between a statistically significant result and an economically meaningful result? Here's a quick example. Suppose there is a pilot test on a new drug. The drug actually reduces the number of days taken before a full recovery. All right. So the company starts preparing to produce it for large-scale commercial distribution. However, the active ingredient is scarce. Oh, we're going to talk about scarcity in our economics readings, and expensive to acquire. In addition, pharmaceutical companies always have to worry about the FDA and go through that long process. All right. So in the end, the company decides not to pursue the drug because it lacks economic feasibility. So something might be statistically significant, but it might not have an economically meaningful result. And this can occur from a variety of factors, but the reading mentions 3: because of taxes, because of differences in risk, and because of costs. And so let's go ahead and look at another just quick example. Suppose that there's a US-based company who wants to expand its product lines into Iceland. Financial manager for this US-based company performs a statistical test and determines that earnings per share will increase by a statistically significant amount if, in fact, we expand this product line into Iceland. However, a couple of things that we need to consider. There's an export tax that cannot be quantified in the test. In addition, the risk of selling the product line is higher in Iceland than it is in the United States. Of course, different countries have different political risks and different political systems, and so there might be political risk in Iceland that's difficult to quantify in a statistical test. And then the cost of distributing this product line, let's just say it's unknown in Iceland. So if you combine those three, it's probably a good idea for the US-based company to reject this expansion into Iceland, even though statistically, from a statistical standpoint, EPS will go up. Now, one of the other consequences here is that when a financial researcher collects large samples, they might produce results that have statistical significance but not much in the area of being applied to an economic or an investment decision. All right, what about the p-value? How does that fit into all of this hypothesis testing? Think of it this way. P-value is the lowest level of significance, lowest level that we can reject the null. What we're going to do is the exact same thing that we did in critical values, comparing them to the test statistic. And so we're going to decide whether or not our p-value is either greater or less than our level of significance. For example, 5% is a commonly chosen p-value because that relates to 95% confidence and a 95% confidence interval that we talked about in the previous readings. And we're going to see if our p-value falls below that number, then we're probably going to reject the null hypothesis. If it lies above that number, we're probably going to reject the null hypothesis. Those are for one-tailed tests if we're working to the left or working to the right. And then we're going to sum the probabilities for a two-tailed test. Let's look at a quick example here. Let's suppose we have a sample of 50 CFA charter holders, average IQ of 105. Previous studies shows that IQs are normally distributed, so that's important. Remember, we have to have a normal distribution so we can have a bell-shaped curve. Standard deviation of approximately 20. So 5% level of significance. Is the mean IQ of CFA charter holders greater than 100? All right, so what's your first thought about that question? Your first thought is, wait a minute. 105 is greater than 100. The answer to that question ought to be yes. But not so fast. It must be compared considering the standard deviation and the sample size. All right, so our test statistic, we're going to use that formula there, x bar minus 100. So there's the 100 that we came up with. That was our belief. Remember, that could be 99 or it could be 101. And then x bar is the 105, which is the result of the sample. And so in the numerator, remember I said I want you to think of it in terms of maybe a mean return or maybe a difference in returns. Well, that's what we're doing here. We're saying, look, the sample says 105. I think it should be greater than 100. I'm not sure whether it is or not, but 100 is what I think is the IQ of these 50 charter holders. And so let's go ahead and put that in the numerator. So 105 minus 100, that's going to be the 5. And then we have to divide by the ratio of standard deviation to the square root of time. And so we get a test statistic of 1.7, and we'll just round up to 7. All right? So what do we do with it? There's the first part. There's the first part of these steps is to set up the null and then to compute the test statistic, which we just did. All right, now how do we make this decision? What we're going to do is we are going to find that, here, let me go back here. What do we have? 1.77. I rounded for a specific purpose. What we're going to do is find that 1.77 in the body of this Z table. So what we're going to do is run our fingers down the left-hand column. So notice you have Z starting at 0.0. So run your finger all the way down until you find 1.7. And then run your finger across until you find the 0.07. So you run your finger down to get to 1.7. And then you run your finger across to get to 0.07. Add those two together. So 1.7 plus 0.07, that gives your test statistic, 1.77. And you find that intersecting number, and that's 96/16. So that's the cumulative probability. Subtract that from 1, and we get 0.0384. And the fact that our p-value, 0.0384, means that it is less than our, where did I go back here? Using a 5% level of significance, we computed a p-value of about, can I round up to 4%? So the fact that 4% is less than 5% means that we have evidence to say that, yes, 105 is statistically greater than 100. So we're going to reject the null hypothesis at the 5% level. Now, let's go back to our z-test and do it from a critical value standpoint. What we need to do is we've decided that we want to do 5%. So what we're going to do is find 1 minus that 5%, which is 95%. We're going to find that inside the table. And so if you run your finger down until, actually don't run your finger down, just look at the table and try to find 95% somewhere in the body of the table. And you can clearly, top left is 50% and bottom right is almost 100%. So somewhere in there, you're going to get 95%. So look there, you get 0.9505. And that's the intersection of 1.6 and then 0.5. So our critical value is 1.645. And in the slide deck, I have the actual number from an Excel program. And so what was our critical value back here? It was 1.76. That is greater than 1.65. And so once again, we have sufficient evidence to reject the null hypothesis. So you see how we did this. This is a summary of all of these previous slides here. We have this test. We think, let me go back here. We think that this average IQ of a 105 is statistically greater than 100. All right, and so sure, 105 is greater than 100 mathematically, but is it statistically greater than 105 given the sample size and given the standard deviation? And with the p-value, we said yes, it is, because 0.384 is less than 0.05. And with the critical value of the z distribution, we say yes as well, because make sure I get that number right, 1.77 is greater than 1.64. And so the summary here is that you can, when you have this test, you can use either the critical value approach or the p-value approach, and you'll arrive at the same conclusion. All right. Identify appropriate test statistic, interpret the results for a hypothesis test when we know some things and when we don't know some things. You should remember a similar learning outcome statement in the previous reading. All right, so a couple of scenarios here. If the underlying variable is normally distributed, so that means it has a bell-shaped curve, what we want to do then is use the z-statistic. And when the variance is known, then we can just substitute the variance in the denominator of the z-statistic. That's why there's the lowercase sigma in the numerator of the denominator. How's that if you're paying attention? And so note there that the sigma is the standard deviation of the population, which is known. And then we're going to do the same thing that we just did in the previous example about the IQ. We calculate that z-score, and we're going to compare it. If we have a 5% level of significance, we'll compare it against 1.96. Now, of course, the next step, the next scenario, if the first scenario is when the variance is known, then we've got to go if the variance is unknown. And then all we do, of course, is substitute the sample standard deviation in the denominator. And then we swing back to the t distribution. So we'll use a t statistic when the variance is unknown because we're using the sample standard deviation, which then must mean that we go back to the t distribution. And we do the same thing that we did back in the IQ example. Now, sometimes a researcher is going to want to know whether or not two populations have the same mean. Let's take an example that's probably not accurate. I might say something like, hey, I think the mean return on a treasury bond mutual fund is going to be the same thing as the mean return on an aggressively, actively managed equity mutual fund. I might say that those two mean returns are identical. We don't think they are, so we can arrange a test like this. And we can say that the mean of the T-bonds is the same as the mean of equity securities. And so the null hypothesis is going to be that the mean on the T-bond minus the mean on the equity mutual funds is going to be equal to 0. And that's what I have at the bottom bullet point there on the slide. All right, so the basic situation, two independent random samples. So you have a sample of the treasuries and you have a sample of the equities, and the means and the standard deviations. Now, of course, my example is probably not too accurate because one of the assumptions that we're making in there is that the two samples have identical variances. And so that kind of throws that example out the window. But if I said something like, hey, let's look at the mean returns from a treasury bond mutual fund that's managed by Jim, by me, and let's compare that to a treasury bond mutual fund that's managed by Ed, then we can make a distinction between Jim and Ed's performance. And the standard deviation in those two samples, since they both contain treasury bonds, is probably identical. Here we're going to use the T statistic. And so the numerator is exactly what we've been saying all along. We're going to take the difference between those two means and then divide by some kind of standard deviation. And that SP is going to be what's known as a pooled standard deviation. And it's really just a weighted average of the two standard deviations of the two samples. Now, we've got to be careful here when we're comparing two means. Our degrees of freedom are just a little bit different. What we're going to do, remember, degrees of freedom in the last reading and earlier today, the degrees of freedom is just n minus 1. We take n and we subtract 1 because n is the sample size. But now we have two sample sizes. So we have to do n1 plus n2, right? We have those two sample sizes. And then we need to subtract 1 from each. So it's really n1 minus 1 plus n2 minus 1. And so it's easier to write it as n1 plus n2 minus 2. And we perform the same statistical exams, compare them against critical values or its p-values, just like we did before. How about with large samples? So back here with small, let me go back here. With small samples, we're going to use T. With large samples, we're going to use Z. So it's almost a virtually identical test. But remember, small samples T, large samples Z. And you compute the statistics just like we always have. Let's go ahead and look at an example here. Let's suppose we want to establish whether there's a difference between a pre-dividend and a post-dividend share price within an industry. All right, so we've got prices before the dividend, and then before the dividend announcement, and then we have prices after the announcement. So the cool thing here about this kind of a hypothesis is that there's no dividend that is being paid. So nothing changes except in the middle. In the middle, there's a dividend announcement. And so the board of directors says, all right, today we're going to pay a dividend in 15 days or 20 days, whatever that number is. So what we're going to do is collect 7 days before, 7 days after. So this is paired data, and the analyst can perform this test on the data. And so here's the test statistic used, and we have similar formulas here where we have that mean dividend payment, and we'll use the sample standard deviation of the paired data, and that's the formula down at the bottom. What happens if we want to substitute the mean that we've done so far with T and Z, and we want to do some tests on the variance? So when we do variance tests, we bring in the specter of a chi-square. So a chi-square test is used to establish whether a hypothesized value of a variance is equal to or less than or greater than a true population variance. So look at that null hypothesis. We're saying that the variance, the null is that the variance is equal to some hypothesized value. And there's the chi-square distribution. It's n minus 1, so there's the sample size, times the sample variance, divided by the hypothesized population variance. All right. Now, suppose we have two independent random samples, size n1 and n2. And they each have their own mean and they each have their own standard deviation. What we want to do is we have sample variances from those two populations, and we want to know whether or not those two sample variances are equal based on our knowledge of the population variance. And so if we take the ratio of those two sample variances, we get an F distribution. So here's the first lesson. Let's go back here. Chi-square is used to evaluate the difference between a population variance and some value of the variance that you believe in. All right, that's chi-square. Think of chi-square as kind of like a normal distribution squared, because the variance is a squared number, all right? Now, when you have two populations, then you can divide those population variances by substituting sample variances in there, and that's the F distribution. All right, here's a good example. 15-year period between 2000 and 2015, monthly return had a standard deviation of 5%. All right, there's a 5% standard deviation. We don't really care what the monthly return is right now because we're going to measure variances. Matthew Brown wishes to establish whether the standard deviation during that period adequately describes the long-term standard deviation. So think about this. He collects data on monthly returns between 2016 and 2017, computes a monthly standard deviation of 4%. All right, so think about what's going on here. For 15 years, the observed monthly return is 5%, but then in the subsequent 2 years, did I say monthly return? The monthly standard deviation is 5, and then in the subsequent 2 years, the monthly standard deviation is 4%. So carry out a 5% test, so there's our level of significance, to determine if the standard deviation computed in the latter 2-year period is different from the 15-year period. All right, so there's our hypothesis that the variance is equal to 0.0025, which is the 5%. So standard deviation is 5, so you do 5 squared, so that gives you 0.0025. 24 months, n is 24, so that's the sample that is being tested. So our test statistic is the chi-square, since we are evaluating the variance. And so we can compute that as 14.72. What else do I want to say about this? Notice in the numerator you have 0.0016. That's down here at the bottom bullet point, our monthly standard deviation of 4%. Square that to get the variance. 4 times 4 is 16. So you get a chi-square of 14.72. And this is a two-tailed test, because how did we word this back here in the previous? Carry out a test to determine if the standard deviation is different. That means it could be greater than or it could be less than. So that's a two-tailed test. If that last sentence were to have said, compute to determine if the standard deviation computed in the later period is greater than or less than, then it would be a one-tailed test. All right, so we do the two-tailed test. We get our test statistic. What we have to do, just like we did back with Z and just like we did back with T, is to find the critical value. Now, since it's a two-tailed test and since we have a 5% level of significance, we're going to have 2.5% in the left-hand part of the distribution and 2.5% in the right-hand distribution. So what we're going to do is we're going to go up to those top columns and we're going to look at the 97.5 and the 2.5 columns. Those are our columns of reference because those columns will reflect 2.5% in the upper right tail and 2.5% in the lower left tail. What we're going to do is try to find if our test statistic is inside or outside of that range. So our degrees of freedom, what was our N? N was 24, so degrees of freedom is 23. So let's run our finger all the way down under degrees of freedom. We hit 23. We're going to stop as we go across the table once we hit the 975 at 11.689. All right. Then we're going to run it all the way over until we get to the 0.025. And we're going to hit, what is that, 38.076. What was our critical value? Our critical value was 14.72. So that lies somewhere in between those two critical values. Our test statistic lies between the two critical values, which means that we cannot conclude, hold on, let me go back here. We cannot conclude that the 4% standard deviation from 2016 to 2017 is any different, statistically speaking, from the 5%. In order for us to make that conclusion, that test statistic had to have been outside of that range. So what's our conclusion? The latter standard deviation value is close enough to the 15-year value of the standard deviation for us to say that we have insufficient evidence to reject the null hypothesis. How about parametric and non-parametric tests? Parametric tests are statistical tests, which we've been doing during this entire slide deck. So we make some assumptions about the distribution of the population. And so far, these for means, those are normal distributions. For chi-square, those are chi-square distributions. And so we can use the z statistic or we can use the t statistic. But non-parametric tests are called distribution-free tests because we don't really know what the distribution is. Let me give you an example of a non-parametric test. Suppose that you go to the doctor. For example, I take my children to the doctor regularly because they hurt their shoulder or their knee or their ankle. And the doctor comes in and says, hey, tell me what your pain level is between a 0 and 10. Pain level, if you have no pain, it's a 0. If you can't stand it, it's a 10. And so my children, they're not the toughest children out there. They always said, oh, it's about an 8 or it's about a 7. But there's really no way to tell the difference. Even though it's in deciles, there's really no way to tell the difference. What a 14-year-old can tell the difference between an 8 and a 7. And so some of these non-parametric, these distribution-free tests occur because the median is probably more relevant than the mean. Or if you have a small sample size, like my son, just one sample size. Or if you have these natural ordered categories like, 0 through 10. Or suppose you're watching a horse race, the Kentucky Derby next year, and you see, the first horse wins and the second horse loses by a length and the third horse loses by 10 lengths. So they still come in first, second, third. But there's 1 length between first and second and 10 lengths between second and third. And so you have no idea what kind of distribution that is. And that really takes us through the statistics portion of this reading. But we do have to finish up with technical analysis. So we'll do that next.